All right, we are going to start chapter 4 by talking about Riemann sums. So let's just jump into this first example. We've got a car that's traveling so that its speed is never decreasing during a 12-second interval. The speed at various moments in time is listed in the table below. A graph of the data is also provided. All right, so using 3 subintervals of equal length, estimate the distance traveled by the car during the 12 seconds by finding the areas of the 3 rectangles drawn at the heights of the left endpoints. This is called a left Riemann sum. Okay, so let's start back here at the beginning. We're going to use 3 subintervals of equal length. All right, so if our time span goes from 0 to 12 seconds, if I divide that by 3, then I have 3 intervals of equal length of 4 seconds. So one of my intervals is from 0 to 4, one is from 4 to 8, and the other interval is from 8 to 12. So I've got 3 intervals, and each of those intervals has a length of 4 seconds. All right, and then we're going to find the areas of the 3 rectangles drawn at the heights of the left endpoints. Okay, so my first interval is from 0 to 4. So the endpoint on the left is my 0. So I'm going to draw a rectangle that has a height of that left endpoint over that whole interval. So it's going to look like that. Okay, and then between 4 and 8, my left endpoint is the 4. And so I'm going to draw my rectangle at the height of time 4, which is going to be 21. And then my last interval from 8 to 12, the left endpoint of that interval is 8. So the height of my rectangle is going to be at the data point where my time is 8. So I'm going to estimate the distance that this car travels by finding the area of these rectangles. And it makes sense that I'm finding the area of these rectangles, and that's going to represent the distance, because we all know that distance equals rate times time. And this rectangle right here is representing a time of 4 seconds at a rate of 5 feet per second. So if I travel 4 seconds at a rate of 5 feet per second, then I have traveled for 20 seconds over that interval. And then my next rectangle is an interval of 4 seconds again, and the rate is 21. And then the third interval, or third rectangle, is the length of the interval is 4 again, and the speed is 45. And another way to think about this, if you have intervals of equal length here, then another way to think about it is each of the lengths of these rectangles is 4, and then you can just add the heights together like that. It's like factoring a 4 out of that first line, and that's what you're left with. You're always welcome to write it like I did on this first line, but most of the time when people get used to these types of problems, they will write it as just the length of the interval times the sum of the heights of all of your rectangles that you found. And if you happen to type that into your calculator, then you're going to get 284. And our units would be feet. So this left Riemann sum is an estimate that the car traveled 284 feet. And this is actually an underestimate, because if you were to connect all of your data points, the exact distance that the car travels is going to be the area between this curve that I connected the data points with and the x-axis, but these rectangles are just an estimate of that area. Okay, let's look at part B. Using 3 subintervals of equal length, estimate the distance traveled by the car during the 12 seconds by finding the areas of the 3 rectangles drawn at the heights of the right endpoints. This is called a right Riemann sum. Okay, so again, we're still going to use these intervals for these 4-second intervals here, but this time between 0 and 4, I'm going to use the data point on the right end of that interval, so at 4. So at time 4, the car is traveling 21 feet per second, so my rectangle that I'm going to use is going to have a height of 21. All right, the next interval from 4 to 8, on the right side of that interval, between 4 and 8, the speed is 45. My height is 45. And then between 8 and 12, the right side data point is at time 12, and the height is 65. The speed is 65, so the height of the rectangle is 65. So now I'm going to use these blue rectangles to estimate the distance that that car travels. So I'm just going to jump to this second line that I did up here in part A. So each of my intervals has a length of 4, and the height of the first rectangle is 21. The height of the second rectangle is 45, and the height of the third rectangle is 65. And if you type that into your calculator, you get 524 feet. And this is obviously an overestimate because the areas of these rectangles include more area than just the area between the curve that connects the data points and the x-axis. A lot of times you will just be given a table of values and not the graph. I wanted to provide the graph for you on this first example just so you can kind of visualize what's going on. But I want you to look back at the left Riemann sum. Notice that on our intervals right here, for the left Riemann sum, we just took the data points on the left side of each of the intervals, the 5, the 21, and the 45. And then when we did the right Riemann sum, we took the data points on the right of each of the intervals. Okay, I'm going to start with a clean graph to do part C. And you may want to grab a different colored pen as you're doing this. That might be helpful. Using 3 subintervals of equal length, estimate the distance traveled by the car during the 12 seconds by finding the areas of 3 rectangles drawn at the heights of the midpoint of each interval. This is called a midpoint Riemann sum. All right, so remember our intervals are still 4 seconds long. So between on the first interval from 0 to 4, the midpoint of that interval is at time 2. So I'm going to draw the height of my rectangle at the y value of time 2. And then between 4 and 8, the midpoint of that interval is 6. So on my second interval, I'm going to draw my height at the data point when time is 6. And then between 8 and 12, the midpoint is 10. And the speed at time 10 is 54 feet per second. So I'm going to draw the rectangle height of 54. And this is a much better estimate than either the left Riemann sum or the right Riemann sum, because you can see that each rectangle, part of the rectangle is over the curve, but part of it is under the curve. So it's still not an exact distance that this car is going to travel, but it's at least a whole lot better because part of my rectangle is above the curve and part of my rectangle is below that curve, and they come close to canceling each other out, but they won't exactly. All right, so now I just need to add up the areas of those 3 rectangles. So once again, each of my rectangles has a length of 4, and then the heights of these rectangles are 12, 32, and 54. And if you type that into your calculator, you get 392. So the car traveled 392 feet by this estimate. And if you didn't have the graph, then you could just mark your intervals on your table and then pick the midpoints of each of those intervals. All right, let's look at this last part. There are really three types of Riemann sums, and I group the left and the right Riemann sums together as one type. So there's the left and the right Riemann sums, there's the midpoint Riemann sum, which we just did, and then the third type of Riemann sum is a trapezoidal sum. And a trapezoidal sum is just what it sounds like. We are going to draw trapezoids and find the area of those trapezoids. Okay, so again, on part D, we're still using 3 subintervals of equal length. So each of our intervals is going to have a length of 4. It may be helpful to draw those on your graph. And then we're going to make a trapezoid out of each one of these intervals. So my first trapezoid is going to look like this. And then my second trapezoid will look like this. And my third trapezoid like that. And this is also a much better estimate than just a left Riemann sum or a right Riemann sum. And it's, again, not going to be exact because these data points are not perfectly linear, but it's going to be a pretty good estimate. All right, before we jump into this, we need to review the formula for the area of a trapezoid. And the area of a trapezoid is 1/2 the height times the sum of the bases. And these trapezoids are kind of turned 90 degrees from probably what you're used to seeing them. The bases of the trapezoid are the 2 parallel sides. So my base of this first trapezoid, here's base 1, and here's base 2. So that means that the height of the trapezoid is the length of the interval. And then the second trapezoid, the height, again, is going to be the length of the interval. And here's base 1, which is going to be 21, and base 2 is over here and this is going to have a length of 45. All right, so let's find the area of these 3 trapezoids. So my first trapezoid is going to be 1/2 from the formula. The height of the trapezoid is 4, the length of the interval, and the length of the 2 bases in this first trapezoid, the lengths are 5 and 21. Okay, and then my second trapezoid, again, I'm going to use the 1/2 as part of the formula. The height of that trapezoid is 4, and then the sum of the bases of this second trapezoid, here I'll number the trapezoids for you, the sum of those bases is going to be 21 and 45. And then my third trapezoid is going to be 1/2 times 4 times, and then the sum of those bases is 45 and 65. All right, and then we would add all that up and type it into our calculator. Again, there's a little bit of a shortcut. Notice that you have a 1/2 and a 4 on each of these 3 areas that we're trying to add up here. And this is just because our intervals are of equal length. Sometimes we will have intervals that are not equal length, and you'll have to write it out like this. But if your intervals are of equal length, then we could write this out as 1/2 from the formula. The height is 4, and that's the same for every single trapezoid right here. And so then we're just left with the sum of the bases. Oops, and this should have been 21 plus 45. Sorry about that. All right, so what's left is 5 plus 21 plus 21 plus 45 plus another 45 plus 65. So it ends up being 5 plus 2 times 21 plus 2 times 45 plus 65. And that would take less time to type into your calculator. And also, if you're not given the graph, then notice up here that if we are just taking it from your data table up here, we've got the 1/2, the 4 is the length of the interval, and then this first, okay, I'm going to circle the speed at the endpoints of each interval. Notice I use the 5 once. I use the middle data points, the 21 and the 45, twice each. And then the last one, which is 65 in this case, I only used once. And that's a pattern that you'll always see in these problems as long as your intervals are of equal length. All right, and if you type that into your calculator, then you get 404 feet. And if you'll notice that, if you'll look back at the midpoint sum, it was 392, and the trapezoid is 404. Those are usually going to be very similar to each other. They're going to be very close because they're both fairly accurate. And for this particular set of data, we don't know which one is more accurate, and that's okay. They're not going to ask you that for data that looks like this. And on the AP exam, and when I give you quizzes and tests, I will always tell you which type of Riemann sum to use. You're never going to have to pick which one to use. I'll always tell it to you. Okay, so let's try another example. This time we're given the function f of x equals x squared plus 1, and we're going to estimate the area bounded by the graph of the curve and the x-axis between 0 and 2 by using some specific Riemann sums. On all of these Riemann sums, we're going to use 4 equal subintervals. So let's go ahead and graph f of x equals x squared plus 1. If x is 0, f of x is 1. If x is 1, f of x is going to be 2. If x is 2, f of x is going to be 5. And this is basically the right side of a parabola that's been moved up 1 unit. That's not a great graph, but hopefully you get the picture. So I'm trying to estimate the area between 0 and 2, but it's asking me to use 4 different subintervals. So I'm going to draw in these 4 equal subintervals. So the length of each interval in this case is going to be 0.5. It is going to be worth it to find the y values of these other 2 points right here at x equals 0.5 and 1.5. And this one's, I mean, you could probably do this in your head, but probably the easiest thing to do is to type y equals x squared plus 1 into your y equals and set your table to start at 0 with your delta table going up by 0.5 and then just filling in the chart, copying that table from your calculator onto your paper. All right, so at x equals 0, we had 1. If you look at the table in your calculator, when x is 0.5, f of x is 1.25. When x is 1, f of x is 2. When x is 1.5, f of x is 3.25. And then we have the 0.2, comma 5. All right, so if we use a left Riemann sum, then that means that in this first segment right here, I'm going to draw the height of my rectangle from the left endpoint. And then on the second interval, I'm going to use the left endpoint of that interval to draw the height of my rectangle, and so on. Okay, so these red rectangles represent my left Riemann sum. So if I find the sum of those, the areas of those rectangles, each of these rectangles has a length of 0.5. And then my heights are 1, 1.25, 2, and 3.25. And notice that if I use the data from the table that I wrote right here, my left endpoints, I'm using the first f of x value, but not the last f of x value. Because if I'm using a left Riemann sum, then I want to take the very first data point, and I'm not going to use the last one. And if we type that into your calculator, you get 3.75. And there are no units on this, so they didn't give you any units on this, so you're not required to put units. If you wanted to put units squared, you could, but you don't have to. All right, and then is this an underestimate or an overestimate, and explain your answer. So obviously this is an underestimate because those rectangles fall below the curve, but that's not good enough reasoning on the AP exam. It's an underestimate because f of x is increasing. And for any increasing function, if you use a left Riemann sum, it's always going to be an underestimate. But a left Riemann sum is not an underestimate for every single function. If you have a function that's decreasing, then if you draw rectangles using the left endpoints of your data points, then a left Riemann sum for a decreasing function is going to be an overestimate. Now, this is not something that I would recommend memorizing, but you can easily sketch the graph. So if you're ever asked, if you have a decreasing function and use a left Riemann sum, is that going to be an overestimate or an underestimate? Well, just draw yourself a decreasing function and draw in those rectangles on your left, on the left sides of each of those intervals, and you'll see that it's an overestimate. If you can and want to memorize it, go for it, but my brain is too full to memorize all of those things. Okay, I'm going to switch colors here, and we're going to do a right Riemann sum. Okay, so for a right Riemann sum, I'm going to take that first interval, but I'm going to draw the height of my rectangles on the right side of that interval. So now if I find the sum of all of those rectangles, again, my length of each rectangle is 0.5, and then the heights of my rectangles are 1.25, 2, 3.25, and 5. And notice that if I look at my data table down here, for my left Riemann sum, I used the last data point, for the right Riemann sum, I used the last data point and not the first data point. A left Riemann sum is going to use the first data point but not the last. And a right Riemann sum is going to use the last data point but not the first. And this will become much easier as we go along. And if you type that into your calculator, you get 5.75. And obviously this is an overestimate because the rectangles fall all above that curve. But the explanation that the AP exam is going to expect is because f of x is increasing. And we used a right Riemann sum. So for an increasing function, a right Riemann sum is going to estimate it. But if you have a decreasing function, then a right Riemann sum, where we draw the heights of the rectangles on the right side of each interval, is going to be an underestimate. So again, you just kind of need to sketch the graph. Okay, Next, we're going to do a trapezoid Riemann sum. Okay, so I'm still using 4 equal subintervals. But now I'm going to make trapezoids. Okay, so remember that the area of a trapezoid is 1/2 height times the sum of the bases. Okay, so if I want to find the area of this first trapezoid, I've got 1/2 from the formula. The height of the trapezoid, remember, is the length of the interval. So that's 0.5 or 1/2, doesn't matter what you write. And then the sum of the bases is going to be 1 and 1.25. My first trapezoid. Okay, the second trapezoid, the sum of those bases is going to be 1.25 and 2. The third trapezoid, the sum of those bases is going to be 2 and 3.25, and then the fourth one, the sum of those bases is going to be 3.25 and 5. So this is where we can do the shortcut of taking the first data point plus twice the middle ones. So the 1.25, the 2, and the 3.25, and then your last data point. All right, so I took the 1 once, and then the middle ones, 1.25, 2, and 3.25 all twice, and then the last one. And if you type this into your calculator, you get 4.75. For that estimate, and you can see that that's much more accurate. All right, for whether a trapezoid Riemann sum is an overestimate or an underestimate completely depends upon the concavity of your graph. So if you have a graph that is concave up, like this one, then when you pick 2 data points and connect them, then that trapezoid that you drew is going to be bigger than the actual area under the curve. So this is an overestimate because f of x is concave up. So for over-underestimate of trapezoid sum, it's dependent upon the concavity. If you have a function that is concave down, then when you draw your trapezoid, the trapezoid is going to be an underestimate. And once again, I don't suggest memorizing this, I just suggest being able to draw it. So just kind of to review, for left and right Riemann sums, the overestimate, underestimate has to do with whether the function is increasing or decreasing. But for a trapezoid Riemann sum, the over or underestimate has to do with the concavity of the graph. Okay, last part is to do a midpoint Riemann sum with 4 equal subintervals. All right, with the midpoint, you have to remember that you've got to go to the middle of your interval, and that is where the height of your rectangle is going to be. So for this first interval between 0 and 0.5, my height is going to be about right here. And then my second rectangle is going to look about like this. And then in the middle of 1 to 1.5, the height's going to be about right here. And then there's my last one. All right, now if you're given an actual equation, you can't just estimate the heights of all of these rectangles right here. So we're going to have to use a new data table right here. and the x value at the middle of the first interval is going to be 0.25. And then the next interval between 0.5 and 1, halfway in between that, is 0.75. And then 1.25 and 2. So the easiest way to get these f of x values is, again, to use your table. So you should already have y equals x squared plus 1 in your y equals. So switch your table settings, go to table set, and start with x equals 0.25, and then your delta table is still going to be 0.5. So if you copy that from your calculator, or just use mine, you get 1.0625, 1.5625, 2.5625, and 4.0625. All right, so our midpoint, I'm going to write it up here because there's more room. Our midpoint Riemann sum, the length of each rectangle is still 0.5, but now the heights of my rectangle are these values in my f of x column. 0.5625, 2.5625, and 4.0625. And if you type this into your calculator, you're going to get 4.625. And again, you should expect that number to be very close to the number that we got for the trapezoid Riemann sum. All right, so those are your three basic types of Riemann sums: left and right Riemann sum, your midpoint Riemann sum, and then your trapezoid Riemann. All right, last problem. In order to determine the average temperature for a day, a meteorologist decides to record the temperature at 8 times during the day, as indicated by the data in the table. Use a Riemann sum with the intervals indicated in the table to estimate the average temperature during this day. All right, the difference between this problem and the other ones is that we're trying to find the average of something, and when you see average, you may be tempted to just add up all of these values and then divide by the number of values, which in this case, there are 8 values in this data table. But that's not going to give you an accurate average temperature, because the 42 degrees was taken sometime during the interval from 12 a.m. to 5 a.m. That was over a five-hour period. But the next interval is only 2 hours. So we've got to take that into account. So the way that we want to do this is for 5 hours, where it was around 42 degrees. And then for 2 hours, we can think of it as being about 57 degrees. And then the next interval was, again, 2 hours, and that temperature was 72. The next interval is a 4-hour interval, the temperature of 84. The next interval was 3 hours with a temperature of 89, and then another 3 hours, temperature of 75, 2 hours, the temperature of 66, and then 3 hours with the temperature of 52. So that is the sum of all of our temperatures right here. But don't forget to divide by the total amount. But the total amount is not 8, the total amount is 24 that we're dividing by, because it was over a 24-hour period. If you type this into your calculator, in the numerator you get 1,584. And the only reason I'm telling you that number right there is that if in the future, when you're trying to find the average of something, if you end up with a huge number like this, hopefully you look at the reasonableness of the situation and look at these temperatures and say, well, there's no way that the average could be 1,584 degrees. Well, that's the total number of degrees over that whole 24-hour period. So you have to divide by 24. And when you do that, you get 66 degrees. And that's a very reasonable answer just by glancing at all of those different temperatures and thinking, yeah, that's reasonable that the average temperature could be 66 degrees on that day. All right, that is it.